Preparation for the test, you want to make sure that everything in your notes is clear, and that you can redo all the problems that we covered in class and in the homework. And so, going back through your yeah, we can. But a lot of people wait until the end to do it. So I don't want to go over it until people have had a chance to try it. Unless has everybody tried it?
Tried what?
The old test.
Not all of it.
Yeah, let me wait a little bit. But if you have, you can ask me during office hour too. But you should treat the sample test as like a real test. See if you can do it with a little bit of time pressure. But going back to through the course, was there anything that wasn't so clear so far? Things that you want me to talk about? Or problems that we encountered?
On the first chapter, you made like this picture. It's like properties, and then underneath it is structure.
Yeah.
And then observation and theory, and then pattern. Can you explain that?
Okay. Well, we're most interested in the properties of matter.
Yeah.
And so, basically, from the properties of matter, one way you could do that is you could just do observation. So if you're ever interested in any kind of matter, we just observe it and see what the properties are. And so this is just experimental work. So if I'm interested in properties of some solid, I'll just take a whole bunch of observations, a whole bunch of measurements on that solid. But can we do everything in that manner? No. I mean, yes, we can. I mean, what do scientists do? They observe nature. But if you have to observe everything, is there enough time to observe everything or do? So we have to have a deeper understanding. And that deeper understanding is going to come from having a little bit of theoretical understanding. But sometimes the theory is so complicated that we sacrifice and just say, okay, we'll just go off a pattern instead. And so, in fact, we use all these approaches. We use observation, we use patterns. Patterns are great because with patterns, then we don't have to, we say, okay, this fits this pattern kind of thing, then we don't necessarily have to take measurements or actual direct observations. We just say, well, it kind of fits the pattern and we can make a prediction. Versus, if you didn't understand anything about that piece of matter, you would have to observe everything. It's like this came back to the dogs. If you didn't understand anything about that particular dog, you'd have to observe that dog to understand its behaviors. Well, the same thing with the matter, but then we'll see certain patterns, like certain dogs behave this way, certain dogs behave that way. Is it always correct? We'll see. So patterns can be quite strong. When patterns are very strong, we call them not theory. If patterns are very strong, we don't call them theory. If patterns are very strong, we call them laws. Or theory. Obviously, we know the theory is great. And so this is called the multi-pronged approach to understanding. Well, in trying to recognize patterns and in trying to incorporate theory, then what we see is this. We see, if we want to understand the properties of matter, then if we know what the composition of that matter is. So is it made up of carbon, or is it made up of silicon? It makes it different. There are polymers that are based on carbon versus polymers based on silicon. The polymers that are based on silicon have a much stronger bond and can withstand much higher temperatures. And so there are different kinds of pump oil. I used to use a silicon-based pump oil for my vacuum pump, but it was really expensive. It was, how much was it? I forgot the price. It was like, compared to regular pump oil, the cheaper stuff, which didn't have as high of a temperature. It's like 10 times more expensive. But anyway, so if we know something about the composition, and we know something about the structure, then that means we don't have to take as much observations. Observations is called memorization. You don't necessarily have to memorize it, but you write it down. If somebody didn't write it down or memorize it, then it's lost. But the thing is, in order to better, this is the whole point of that whole discussion, and it's good you asked, because you might say, what was the point of that? And so you want to make sure you understand the point of all that. The point of all that was this. Memorization is important, otherwise you're never going to see patterns. If everything you do is based on not memorizing anything, and that's, so you got to have some stuff memorized, because these patterns take time to develop. The patterns aren't readily obvious, and so it does take some memorization to let your brain put it together. Okay. And so the whole point of that was how we study chemistry. How we study chemistry is you're going to have to apply different methods of memorization, learning patterns, and applying theory. I gave an example much later. I don't know if anybody remembers the example.
Example, which part specifically?
Example of memorization versus theory. I gave multiple examples of memorization versus theory. I don't know if they all clicked or gelled or coalesced together. It takes time for them to gel and coalesce. The multiple examples. One example I gave of memorization versus theory was the catalytic converter in the car. The other example I gave was the blue LED, the search for the blue LED. Another example is the drug development and drug discovery. I didn't write it on the board. I just mentioned that in passing, but I don't know if anybody wrote anything about that down. Yeah. So if you could give examples, it helps reinforce the point of this. The point of this was like, the point of this is also in theoretical physics. In theoretical physics and in chemistry and in drug development, you have two camps. You have the experimental physicists, and then you have the theoretical physicists, all trying to achieve the same thing, but from two different approaches. And so at the Large Hadron Collider, which is in Switzerland, they had a whole bunch of theoretical predictions, which the experimental physicists tried to bear out. It was very interesting, documentary on that. It didn't quite work out the way the theoreticians predicted. It's pretty interesting. But the same thing here. In the search for the blue LED, the red LED was known. It's been known for decades. And the green LED was developed maybe about 10 years after the red LED. And so immediately after that, people were trying to develop the blue LED. This was 50 years ago or something. And so you had two camps, and they aren't totally separate. You had the experimental. The typical way the experimental is they have some kind of target for the composition. They have some kind of target for the structure. And they just mix it and then see what happens. And so the people who were searching for the blue LED, they would try, thousands of different formulations, thousands of different compositions, and see if any of them work. Whereas the theoreticians are saying, okay, let's determine which is the best composition, which is the best structure, and let's see if we can make it. Same thing happens in drug discovery. You have people going out in the rainforest looking for molecules that might show some kind of medicinal behavior, you know, and so these are molecules that have yet to be discovered, but they might have medicinal behavior. Maybe maybe there's some clues, you know, like the indigenous people are using it to treat certain conditions or something like that. And then you have the theoreticians out there, you know, trying to figure out based on, you know, what targets we might have, what good drug candidates there might be. But in reality, you know, science works as a mixture of both. You know, we're not purely theoretical, we're not purely experimental. We try to incorporate all these tools because that's going to be the most efficient means. It means that understanding the theory as best as possible, but not ignoring the memorization thing, not ignoring the fact that we have to just observe some of these things. Does that answer the question on this? All right. What else was confusing? Or problems that were confusing? You know, basically, in preparation for this test, everything should be clear, you know, before the test. If everything's clear, then you can go into the test pretty confident.
Chapter 3, the first one,
Chapter 3?
yeah, the first section. We're round.
When we round numbers?
Yeah, I'm not sure, like, should I round to that thing, or should I round to that?
Okay, how do you go about rounding?
In the book, they round to the thing, right? For the answer.
Well, how we round depends on how many decimal places or how many sig figs we're allowed. So we could take a look at chapter 3 here. The significant figure. That would be, what is that, near the end? The beginning?
So like the homework question number 6.
All right, maybe that's best if we just look at some example problems.
Professor, did you say to memorize the density of wood?
No.
No.
All right, here it is. So for significant figures, we can look at some examples here. But there aren't that many examples here. Take a look in the book for the examples. And so, did the homework go okay as far as figuring it out?
Yeah, because like the answer is in the back, so I just got.
Did your answers match?
Yeah.
Okay, let's take a look at some others.
Generally speaking, isn't the significant figures dependent on the given quantity?
Yeah. It depends on, so we don't always round to the 10. You know, sometimes we'll round differently. It depends.
But that's not hard.
Hmm?
I'm confused.
That's what you're confused about?
Yeah.
Okay. Well, I don't know if you do you want me to do this, or should we look for something else? Does anybody use Khan Academy?
Yeah.
Yeah, so maybe I shouldn't use this one. We should get a different one. That way, if you want to do this one. So there are lots of practice on the internet. So something like this. How many sig figs are this?
4.
4. These zeros preceding are insignificant. But if we were to round that, it depends on how many sig figs we're allowed. If we're allowed 3 sig figs, how would you round this?
0.00301.
Yeah, 2 sig figs?
0.0030.
Yeah. 1 sig fig would be 0.003. Now that's with sig figs, and that's for multiplication and division. However, if we have addition and subtraction, it's based on decimal places. And so for addition and subtraction, we have to be careful. In fact, I just saw this problem yesterday. I didn't really talk about it because so if we had something like 1.0 times 10 to the minus 2 minus 3.8 times 10 to the minus 3, you can punch that out in your calculator. Right? We punched it out in the calculator. That's fine, except there's a problem here, and that's what to do with the sig figs. Because whenever we have addition or subtraction, what we got to do is we either have to get the exponent the same, or we just convert it in decimal form. And so, since these aren't such extreme numbers, I would probably just put it in decimal form. That's going to be 0.010, and then this is going to be 0.0038. And so, if you look at the uncertain digit, this digit here is uncertain. This digit here is uncertain. So if that's uncertain plus 3, this digit is not uncertain. It's this digit here that's uncertain. And so that's going to give us 2 uncertain digits. And so this is going to be, this is minus. So it's going to give me 0.0062. And so I look at this, and then I think, well, how many uncertain digits am I allowed? I'm only allowed 1 uncertain digit, and so how should I round this, if at all? Well, I got to round this. I'm only allowed 1 uncertain digit, so it's just going to be 0.006. If I wanted to, I could do it like this, 0.006 sub 2, indicating that this is an extra uncertain digit. I'm not really allowed that, but I carry it to minimize round-off error. And so that, or the other option is you get, let's say these were a little bit extreme. The other option would be to convert one into let's see, the other, or vice versa. So I'm going to go 10 to the minus 3 to 10 to the minus 2. And so if I convert this into 10 to the minus 2, I'm making this bigger, therefore I have to make this smaller. Minus 0.38 times 10 to the minus 2. Okay, now I can do the same thing, but the exponent has to be the same so that we can see how many decimal places we're allowed. And so the number of sig figs, the number of decimal, where you round it all depends. Are you doing multiplication division? If you're doing multiplication division, you look at the number of sig figs, regardless of where the decimal place is. It doesn't matter if it's the tens place, the hundreds place, thousands place, it doesn't matter. Versus if you're doing addition or subtraction. If you're doing addition or subtraction, it's like this.
In your answer to the first one, if it had instead been 0.0067, would your answer have been 0.007?
Yeah.
Instead of
Right, I would have rounded it up. Right. If it were 0.0067 and I got to drop the 7, then this is going to go to 0.007. I got to round it up. There's always confusion about these types of numbers, though. Like, how many sig figs here?
4.
4 get? Here?
2.
And then it depends on the instructor too, you know. Like for example, 0 versus 0.0 versus 0.00. You know, are these the same? Or are they different? And so, well, how many sig figs here? It's either going to be 1 or infinite. And so if you, I don't know if you do your, let's say you do your, do some kind of like tax thing, and they want it to the nearest dollar. And so if it comes out to 40 cents, you know, at 40 cents, well, if you got to round this to the nearest dollar, what would it round to? 0. So that's where we get this kind of 1 sig fig type deal, because sometimes we'll see 0, it just means that, you know. But 0, technically 0 is 1 over infinity. So how close do you have to get to 1 over infinity? Let's say if you're 1 over 10 to the 12, 1 trillion. Is that close enough to 0? For some people, they'll say, yeah, it's close enough to 0, 1 trillion, you know. It's almost nothing. You know? And so like somebody will ask, okay, what's the cyanide concentration in the air here? And they might say, oh, it's at the part per trillion or less, you know? And let's say we burn some plastic or something. When you burn plastic, you gotta be careful. You don't wanna make poisonous gases, but let's say we made a little bit of cyanide, we burned some kind of plastic there, it's a trillion. And then somebody might say, oh, that's close enough to 0. There's nothing to worry about, you know? And so how close do you want to get to 0? Because when you look at 10 to the 12 versus infinity, are they close? No, not even. These are not even remotely close, right? Let's go to 10 to the 100 and, let's go 10 to the 12,000. Okay, 1 over 10 to the 12,000, that's an incredibly small number. That's what, 12,000 zeros and then a 1? 0.000? Something like that? Or, yeah, actually, 11,999 zeros and then a 1. You know, and so the thing is, but when you compare it to infinity, this is still a huge number compared to infinity. Right? I mean, infinity is a huge number. This is, and so, you know, how close to 0 are you? And so this is why, you know, this is confusing here. So I've kind of, you know, this is more Chem 1A topic, but it comes up. And then there are other things that come up too. The other things that come up are like this. You know, 100 versus 100 point. You know, if there's a decimal place here, or a decimal point, then these zeros are automatically taken as significant, because any zeros following a non-zero with a decimal point are significant. Whereas if there's no decimal point here, then how many sig figs do we have? 1 or infinite. You know? And the same thing like this, 110. This is very tricky, because this actually might be 3 sig figs. It's a little bit confusing. This is either going to be 2 sig figs, infinite, or maybe 3, but to clear it up, you might put a decimal there, or you might write in scientific notation. You write in scientific notation, then we have no problem. Well, 1, 0. And so those are always ambiguous points. And so to really make communication clear, we just rewrite it in scientific notation. That way you don't have to guess, you know. Did the author mean 3, or how many sig figs did the author mean? And so it's not, in other words, this, where you round it to depends on how many decimal places you're allowed for addition and subtraction, or how many sig figs you're allowed in multiplication and division, and that always changes. Since that always changes, we can't predict if it's going to come in the tens place, the singles place, the hundreds place, the thousands place. And so, for example, here, let's say I'm going to do this. I'm going to take 100 plus 0.12. And so, well, that's simple. That just equals 100.12. But what should I round that to? It's going to be 100. Or I do this. I'll take 100 and plus 40. This is ridiculous, but where should I round it to? Well, that's easy. That comes up to 140. Where should I round it to? This is going to round to 100.
Why would we want
You see,
This is the first number.
it's because I'm treating this one as
This one's.
1 sig fig. If I put a decimal place here, then where would I round it? Okay, let's do this. I'm going to do 100 with a decimal place plus 43. What would I round it to? Well, this is easy. This is going to be 143. What would I round it to?
140.
I'd round it to 140 because of this.
Decimal. The 43 is.
Well, I would, okay, this I would just leave 143. But if this were like this, 110 plus 43, then I don't know, because these are kind of ridiculous scenarios, because in science we wouldn't leave it like this because it's too ambiguous. But according to the rules, and the rules, we just, even though the rules aren't perfect, we've got to just follow the rules. And the rules say, well, if there's no decimal point, then the zeros following non-zeros are insignificant if there's no decimal point, right? And so that means this one's not significant. That means 1 is the uncertain digit. And so that means 1, and then this 5 is uncertain, and the 3 is uncertain. So it's going to round to 150. Oh, let me get.
Why was the second zero in 100? Or why was the first zero in 100 be uncertain? Why
Over
was
here?
The last one. Yeah.
Or this one?
That one.
All zeros following non-zeros without a decimal place are insignificant according to the rules. And so we don't know. We don't know how that person said, oh, there were about 100 people at that concert. Well, are you saying that there were 100 and then that means 1, 0, and then maybe 101, 102, 103, up to 109? Or are you saying that there were about 100 plus or minus 50? So it depends on how it's taken. So in science, we don't leave it this ambiguous. This is too ambiguous for us. And so, yes, that's the rules, but those are more for estimates. We estimate there are 100 birds. If you estimate there are 100 birds, how well did you count those? And so you'll see this, yes, but not in chemistry. Maybe you'll see it in other science.
Since it's adding and adding and subtracting, we only care about decimal places. Shouldn't it still be 1?
Well, decimal places meanings, is uncertainty in the hundreds place, the tens place, the ones place.
Yeah.
And so here, shouldn't it still be 153? No, because here we're saying that this is the uncertain. If we call this 2 sig figs,
Yeah.
if we call that 2 sig figs, then this 1 is uncertain. We're allowed 1 uncertain digit.
Okay, so it's the when it's added.
Yeah, and then we're adding it to a 4, which is certain, but the 5 is going to be uncertain, not because of the 4, but because of the 1.
Okay, so that goes for everything before the decimal point. Okay.
But the sig fig rules, it can get complex, and I kind of glossed over them because I didn't want to really get into these little obscure things, because how often are we going to see this scenario pop up? Never, pretty much. We aren't going to see that. The numbers are going to be more straightforward.
So the 100 points plus 43 with the 0 closest to the decimal, would that be an uncertain number?
Yep. Right. See, this would be 3 sig figs. That means 2 of these are certain, 1 is uncertain, so it's got to be this one that's uncertain. If we take that one, that's going to make this 3 uncertain, and we're allowed that. We're allowed 1 uncertain digit. Therefore, we can represent this as 143. Over here, this is uncertain. If we're calling this one, just a placeholder. There are sticklers about this. If you go online and you take a look at some of these, there are a lot like this, a lot of problems like this online. You can find. Okay, let's. The other sig fig questions. Sig figs, I don't, sig figs, if you don't know, write more rather than fewer. You know, the thing that really bothers me is when people round it to 1 sig fig. Now, I know like in elementary school, they might say 4 liters per gallon. You know, that kind of, you know, when you have 1 sig fig there, the uncertainty is too great. You know, it's like 100. You know, if this came out to 149 and you round it to 1 sig fig, then we got to round it to? No.
No, I'm just kidding.
If this came out to 149 and there's only 1 sig fig, we'd have to round it to 100. Okay, what is the round off error in that calculation?
49.
Huge. Round off error is huge. So I hate to see 1 sig fig in conversion factors unless it's absolute, like sometimes it's absolutely necessary, 1 gram per million grams. We had no choice. You know, that was the 1 ppm, although we could call that exact, you know, and that would solve it. I hate to see 1 sig fig in conversion factors unless absolutely necessary, and I hate to see 1 sig fig in answers. If you give me a 1 sig fig final answer, what I'd like to do is like at least subscript it. If you're only allowed 1 sig fig, carry a few extra digits there so we can see how extreme the rounding was. You know.
So for conversion factors, for volume, 1 gallon is equivalent to 3.78541174 liters. How many of those digits do you like us to use?
Just 4 sig figs usually.
4 is fine.
Yeah, but that one's going to be a given. You don't have to memorize this.
3.7.
This is going to be given. So, but usually we'll use 4 sig figs in this class for conversion factors.
Can you go over dimensional analysis for delta T?
Dimensional analysis for delta T. Okay, let's say the temperature of my coffee dropped 20 degrees Fahrenheit. What would that have been in terms of a Celsius drop? In other words, you have to know, am I going to use this equation? Degrees Celsius is equal to degrees Fahrenheit minus 32 degrees times 5/9 divided by 1.8. Do I use that equation? Well, if I did, a lot of people will use this equation because there's nothing saying you can't use this equation. You know, if I were to go ahead and use this equation, that makes total sense to me. I'll just plug in 20 degrees Fahrenheit. Units, the dimensions on this equation, because I don't write the full version. If I wrote the full version of this equation, the full version would have the dimensions included. The full version would look like this. Temperature in degrees Fahrenheit is equal to 9 degrees Fahrenheit over 5 degrees Celsius times temperature in degrees Celsius plus 32 degrees Fahrenheit. And so when we use this equation, all the dimensions will work out, all the units will work out. But oftentimes it just takes up way too much time, so we don't bother committing time. So yes, this should be degrees Fahrenheit. And yes, that is degrees Fahrenheit. And how do I convert it into degrees C? Well, it's because the units over here, which we often ignore. But anyway, I'm going to ignore the units completely. It's going to be 20 degrees minus 32 degrees times 5/9. And so that's going to be minus 12 degrees times 5/9. So let's go ahead and punch that out. Twelve times 5 divided by 9. Oops. This this calculator. 12 times 5 divided by 9. Buttons are not working. Let's try this one. This one looks good. 12 times 5 divided by 9. 6 point, well, how many sig figs am I allowed? Because I got 6.6 bar degrees C. So how many sig figs am I allowed? No, one's incorrect.
Actually, oh,
You see why one's incorrect?
yeah.
Well, first, if you do the subtraction. When you do the subtraction, 20 minus 32 is? Okay, that's the correct number of decimal places because we're allowed to the singles, not the tens, right? Not the first decimal place. And so how many sig figs is that? 2. Times 5. How many sig figs is 5?
1.
Infinite. 5 is infinite. 9? Infinite. Why?
Those are given.
No. They're not, yes, they're given, but that's not the answer I'm looking for.
Because it's the exact ratio.
They're exact. Why are they exact? It's by definition. What is the definition? Remind me what the definition was. This is something we covered in class like a long time ago. What was the definition that made those exact? Yeah, 180 over 100 ratio. Where did that come from? Yeah, but how come that, yes, that's the ratio, but how come it's exact? See, these, well, you might not have written it down, but you see, the more stuff you can have written down, the more times you can see it visually, the more times you'll remember something like this. Why is it exact? Somebody might call you on this. Why isn't it just one sig fig? Or, where I got that one from was 100 over 180. How many sig figs in 100? 1? How many in 180? 2? That's what the rules would say. The rules would say it's 1 sig fig in the 100, 2 sig figs in 180, because zeros following non-zeros with no decimal place are insignificant. They're just kind of placeholders. So if you had like something like 1 million, that would be 1 sig fig, because these are just 1 million plus or minus whatever. So how many birds were there? There were a million birds for sure. That would definitely be 1 sig fig.
So the reason that it's exact is because water boils exactly at 100 degrees, not 101, 102, but exactly 100.
Yeah, it's defined, right? And then what else? You have to add one more thing to that.
Freezing point?
No, the boiling.
The boiling.
You need.
Oh, fair enough.
Where did the equation come from? That's why you need to know. The equation came from the observation. The observation came from the definition. What was the definition? Water boils exactly at 100 degrees C and freezes exactly at 0 degrees C and you see, the situation is, it's okay when you're starting out. It's okay to miss this kind of stuff, but eventually you don't want to miss it, because eventually people are going to challenge you on this stuff. So you might just take it as, oh yeah, it's infinite, or it's 1, because that's what we were taught. But pretty soon, when you get to higher level classes, they don't accept that answer. Uh-huh.
Because the boiling point minus the freezing point of Celsius over the boiling point minus the freezing point of
Yeah, but why is it exact?
Because by definition,
Yeah, it's by definition. So the other part I was looking for is water boils at 100 degrees exactly Celsius and 212 exactly Fahrenheit, because that's how it's defined.
Exactly.
Yeah, it freezes exactly at 32, not 32.1. This is something I mentioned when we were talking about it. It's not 32.1, it's not 30.9, it's exactly 32, you know, so it's by definition. So we know where the equation comes from. If you know where the equation comes from, you don't have to be told, you know. Somebody could have told you this, and you go, well, somebody told me that they're exact. Well, then why are they exact? That's the type of question you'll get, you know, when you go on in science, because they're curious, not because they want to give you a hard time. They're just curious about where it came from. And you might not know and say, I don't know, you know. It's always the way I've used it. That's fine too. You could say, I don't know, you know. But you want to start thinking in terms of knowing. And so how many sig figs am I allowed in this answer? I'm allowed 2. Yeah. So how should I round it? 6.7. So I could use this equation. There's nothing saying I can't use this equation, right? But there should have been an alarm going off. You know, the alarm going off is you're just about to calculate the wrong answer. And so you go to the scientific, you're doing some kind of oral examination or oral presentation or something like that, and you come up with this number. Okay, I just calculated it. Does the calculation look okay? Yeah, calculation looks fine, right? I put in my degrees Fahrenheit, everything looks good. I got the sig figs right, 6.7 degrees Celsius. Oh, I forgot one thing, the negative.
No, that's what I'm asking.
Now it's looking good, right? Calculation's looking good. Unfortunately, it's the wrong answer. This is the wrong answer, but there's nothing no alarm going off, no nothing. This is why you have to. Unfortunately, this one is not so easy.
But the other side?
This happens because in not necessarily in Chem 4, but in Chem 1A, this happens where people use the wrong equation at the wrong time. Even though everything looks right, they'll come up to me and say, you know, what did I do wrong? I used the equation, I plugged in all the numbers, but what did I do? Well, you can't use that equation at this time. And they're going, you know, why? Well, you have to understand the equation more than, you know, just plugging in the numbers. But anyway, I wouldn't have, you know what, I wouldn't have even brought up this equation. I wouldn't even brought up this concept because I think this is too much for Chem 4. I would rather challenge you on the dimensional analysis than on this. But since your book came up with these temperature differences, and it's an important thing to know anyway, so. But that's the wrong answer, right?
So the reason we can't use it is because the equation was created from the observation of 0 degrees Celsius to 100, and now we're entering.
No, that's not the reason. The reason why is, you know, it's because of this. Remember, it's because of the offset. If we look at the Fahrenheit scale, the Fahrenheit and the Celsius are going to be mismatched by how much? If we look at the Fahrenheit scale, the Fahrenheit and the Celsius are going to be mismatched by 32 degrees. They're mismatched because of the 0. Okay, that's looking at the temperature scales, but what we're looking at is we're not looking at the mismatch in the scales. What we're looking at is a temperature change, a delta T. And a delta T doesn't matter where it begins and where it ends. You know, a delta T. So this delta T could have been like this. I'm in the Antarctic. It's 0 degrees Celsius outside. My coffee just dropped from 0 degrees Celsius to minus 20 degrees. Or no, not 0 degrees. 20 degrees Fahrenheit, let's say, down to 0 degrees Fahrenheit in the Antarctic. And so it froze. basically. You know, and so it doesn't matter, the reference point doesn't matter in a change. And so let's say, okay, if you go for a jog, you're gonna go for a 1 mile jog, do you have to start at 0? Oh shoot, you know, I saw this, have you seen those highways where they have the mile markers?
Yeah.
Yeah, okay, are you gonna have to run to the 0 to start at the 0 and then run 1 mile? So I can go from 0 to 1, or can you start at any mile and run 1? You can start at any mile, right, and run 1 mile. And so delta t is different because unfortunately I don't have a good analogy for it, but it's essentially we're just looking at the change. When we look at the change, then we look at the size of the drop. And so it turns into a dimensional analysis problem. And so if it's 20 degree Fahrenheit drop, then we know that for every 180 degrees Fahrenheit, we'll change by 100 degrees Celsius. So 20 times 100 divided by 180. Minus 11.1 degrees Celsius. Then we look at how many sig figs were allowed. Well, it depends on this guy here, because this gets complicated here, right? And I screwed this one up because is this 1 sig fig or 2 sig figs? This is actually 1 sig fig. You're right. Did you catch that and I didn't catch that? Oh, okay. Then, yeah, I made a mistake. Sorry. That was my fault. It should have been 20 point.
So if you just put 20, it would have just been 1 sig fig.
It would have been 1 sig fig.
Okay.
Yeah. All right. Sorry about that. That's what I meant. I was meaning this. So this is 20. I should pick another number like 22. But this is 20, and so this will give me. And so the thing is, it might be, you know, it might be confusing, but all you have to remember is this. If it's a change in temperature, then use dimensional analysis. If we're looking at a specific temperature, then use the equation, the algebraic equation. Uh-huh.
Question. For that equation that it gives the Fahrenheit, will it work for Celsius if we just switch the top and bottom? Because of 180 over 100?
Yeah, well, it's just dimensional analysis. I'm setting this up like dimensional analysis for the degrees Fahrenheit.
Will it work for Celsius?
Yeah, if I wanted, I would flip it over. Yeah.
Can we do another one of those?
A delta T?
Yeah.
So this one, we messed
Okay.
up simply because we missed that word. The temperature of the coffee dropped.
Yeah. Now, if the temperature of the coffee were 20 degrees Fahrenheit, then it would have been frozen. This is correct. If I just said this, the temperature of my coffee is 20 degrees Fahrenheit. What is this in degrees C? This is the correct answer.
Oh, okay.
But since this is a change in temperature, it's different. You know, the delta T is different. Is that okay there, or do another example of just one? Were there other things?
Can we do more sig
Sig
figs?
figs, let me tell you, the most I take off for sig figs is 22 points, 21 or 0.2.
That's 1 sig fig.
So we'll do more. That's good. All right. We'll do more sig figs. Actually, we're going to do more sig figs right now when we talk about this chapter here. So I'll do some sig fig.
So that means it should be rounded to like 0.0, right?
Yeah.
You know, right. Minus 0.1 should round to 0. Minus 0. All right, we're going to revisit atomic theory. This is chapter 5. We already talked a little bit about atomic theory. So I'll continue our discussion. So we talked about Dalton's atomic theory. And then the law of multiple proportions. This is electron. We'll talk about that. And then Rutherford scattering. These are keywords here. Subatomic particles. Proton, neutron, and electron. Isotopes. Nuclear symbol. Atomic number and mass number. Not everything in Dalton's atomic theory is considered valid anymore. There's stuff that they changed, got rid of. There's a new unit called the atomic mass unit, which is U. So we'll talk about that. Atoms don't weigh much, so grams are very inconvenient. What's the smallest unit, metric unit, that you know of for a gram? Milligram? Picogram? Yeah. A picogram is still way too big. Femtogram? Still way too big. So we have to go even smaller. So this is why we have the atomic mass unit. But we got to know how that's defined. The definition of the atomic mass unit, which they don't really talk about here, but that's a learning objective. How do you define the atomic mass unit? You know, how is the kilogram defined? A mass of metal. What, does anybody recall the metals? Platinum. Why platinum? Two reasons for platinum. One, it's really dense. I mean, if they had aluminum, it would be pretty big. But they wouldn't want to use aluminum anyway because of another reason. Why platinum? Why platinum? It does not oxidize easily. It's like gold, it retains its luster. If it oxidizes, like, would they use copper? If they use copper, like a kilogram block of copper, it would look pretty bad, you know, after time. Even though they seal it, did you see how many bell jars they sealed it in? Did I talk about that?
You just mentioned it once.
Yeah. Yeah, well, they're still being extra cautious. Even though platinum and gold are really resistant, maybe some pollutant can get in there. Cause,
3 jars.
3 jars, yeah, it's crazy.
I think they should do 5.
Unless, if they could store it in the perfect vacuum, then they wouldn't have to worry. You know, they keep it in a vacuum, but nobody could use it. Anyway. But it's platinum. So 2 reasons. One, it's resistant to corrosion, and 2, it's very dense. And so platinum and iridium were 2 metals, so you wouldn't have to use a huge block. It's a very small block. Well, do they have some thing, you know, the definition of the U, do they have a little atom stored in 3 bell jars located somewhere in France?
Maybe.
Yeah, you know, a hydrogen atom weighs about 1 U, but it's not exact. Hydrogen weighs 1 U, but it's not exact. What weighs exactly 1 U? Do you know what weighs exactly 1 U? Well, it's some secret. It's hidden in France and it's locked in some vault because nobody knows. Do you know nobody knows what weighs exactly 1 U? Well, actually, people. Nobody knows what weighs exactly 1 U. Because there is nothing that weighs exactly 1 U. If there's nothing that weighs exactly 1 U, then how do you figure out what 1 U is? See, those are the types of questions people are very curious about and people will ask you about, you know, being in science. You
So
know?
should they
Like,
like,
Hmm?
should they just like alter the?
They should alter the definition so that they can store something in France in some vault and many
exactly.
multiple.
Underwater.
Yeah, right. And then it's easier. If there's a physical object, it'd be pretty easy,
It would make more
right?
sense to me at least.
Yeah, it'd make a lot more sense. But well, nonetheless, we need to know how the U is defined. Do we really care about the kilogram? Not so much because the kilogram is so common, right? Everybody uses
Pretty
it.
heavy.
And so it obviously must be, but the U is kind of an abstract unit, and so it's an abstract unit because it's so small, then how do you know what it is? It's one of these things to think about. And so even though it doesn't say how it's defined, well, I actually define and use the U. Well, it depends on how we define it. Some people they define it as a very small unit. But it's not enough. Distinguish between groups and periods. Okay, this is what we're talking about the periodic table. We're talking about behavior of the elements. And so, memorize the names of these and classify them. Anyway, let's just do a little bit and then we'll take a break. Dalton's atomic theory. These are the basic components of Dalton's atomic theory. A lot of these are just kind of, I guess, common sense in a way.
Nowadays, at least.
Yeah. Each element is made up of individual particles called atoms. So the elements are made up of atoms. So nothing. Atoms are indivisible. Can you take a single atom and break it apart to make mini atoms? No. If you break it apart, what does it form? It forms subatomic particles. And those subatomic particles aren't necessarily the properties of copper or whatever else. All atoms of one element are identical in every respect. And so if you have a sample of oxygen atoms or carbon atoms, you know, all the oxygen atoms in water, are they identical? Yeah, if you know about isotopes, it turns out they aren't. So this is one thing in Dalton's atomic theory. They aren't all identical. Some are heavier, some are lighter. But chemically, they're identical. Because when you tasted your water this morning, did the heavier ones taste funny?
Maybe.
Maybe, but maybe you're used to it, right? Do some, you know, maybe that would be good marketing, but it'd be very expensive. You could sell heavy water, you know, rehydrate even better than light water. But you know, it would be true. So if they came after you for the claims, but you know, to get heavy water would be very expensive because you know what fraction or what percentage of the water in here is heavy? A very tiny fraction. It's very small. In fact, we're going to calculate the percentage of these things in water in this chapter. So we can
light water.
Yeah, so we should just sell light water. If you're a marathoner, you just want the light water, we'll just get rid of the heavy water. Something like that. So atoms of one element are different from atoms of any other. So copper atoms are different than oxygen atoms. That's true, right? Atoms of one element combine with atoms of other elements to form chemical compounds. So, you know, would you memorize these components of Dalton's? No, I wouldn't bother memorizing these. You know? Right. It's not worth memorizing these. This is just basic atomic theory. This is what we study in chemistry. But you should know that Dalton came up with the first, he's probably not the first person to propose atoms, but he's the first person to put it together in a scientific theory. And so this is why Dalton's name is associated with atomic theory. How did he come up with a theory? Theories are derived from, you know, was he just walking down the street and all of a sudden came up with a theory? Not necessarily. Yeah, it came from the scientific method. And so this is atoms according to Dalton's atomic theory. An element is made up of atoms. Is that crystalline or amorphous?
Crystal.
Yeah, this has got to be solid, liquid, or gas. Yeah, this looks like a crystalline solid to me. Everything's nice and lined up. Interestingly enough, atoms don't pack this way in the solid. You know, if you were to this is a side note, but if you were to pack atoms in a solid, they don't pack like this. If you were to pack oranges in a box, they don't pack like this. They pack where this one fits in the little well created by the other one here, so we offset this one length, and then we can pack it much tighter. But anyway, this would be an example of crystalline. Atoms cannot be destroyed or created. Is that true? In chemical reactions, it's true. You know, when we combust methane, are we destroying atoms there? No. And so it's true in chemical. In nuclear reactions, it's not true. Yeah. But you know, in Dalton's times, they didn't think about nuclear reactions.
Definitely can't do it with a hammer.
Yeah. All atoms of any given element have the same properties, including mass. No. This is not true anymore, but he said all, let's say all blue is usually used for what? Blue is usually used for nitrogen. So let's say these are two nitrogen. Do you know what red's usually used for? Oxygen. Although it doesn't make sense here because we wouldn't have two nitrogen around an oxygen. So it doesn't, so would we call that the law of the color? No, this is a rule, and rules can be broken without any penalty. So they just broke the rule here. But anyway, all atoms, we should be more specific here. All atoms of any given element have the same chemical properties, but they would have different physical properties because some of them would be heavier, some of them would be lighter. And so, you know, there are heavier water molecules in here. You can't taste it, the difference, but if you were to remove all the heavy water molecules, then that water would be a lot more denser, way more than this. And so, the same chemical properties, yes, but not physical, because one physical property would be density, and the density would be different. Atoms of different elements have different masses and properties. Okay, atoms of different elements may combine in a ratio of small whole numbers to form compounds. So here it's a 1-to-2 ratio, here's a 1-to-1 ratio. 1 red to 2 blues, or 1 red to 1 blue. Example. This is the law of multiple proportions. What came first? Atomic theory or the law of multiple proportions? Yeah, this is kind of weird because normally the law comes before the theory, but in this case the theory was used to predict this law. We had another law that was used leading up to atomic theory, and that was the law of constant composition. Water has a constant composition. That's what led to, well, anyway, getting to this, you guys know this because we talked about this, right? Simple whole number ratios. All right, let's take a break here for 10 minutes and then we'll start up again.